Section 4.2 is about polynomials and their models. Before we start that, let's take a little review from yesterday. When we look at this graph, it says, what is the degree of the polynomial? Well, the degree should be one more than the turning points. So I count 1, 2, 3 turning points. So that means one more would be 4, so it is a 4th degree polynomial. Next, it asks to name the extrema. So I'm going to need local mins, local maxes, absolute min, and the absolute max. So I see that I have minimums here at negative 2.1 and here at about 0.5. I see I have local maximums, the high points here at about 4. And that looks like it. Remember, this is an endpoint, so it can only be an absolute. And it is not the absolute highest nor the absolute lowest, so it is nothing except an endpoint. Now I need the absolute minimum. The absolute lowest looks like it's negative 2.1. The absolute highest goes off the graph, so it is not applicable. Or some people say positive infinity. So just another recap. Remember that the degree is the largest exponent used. The degree also is one more than the number of turning points on a graph, which we just illustrated. And a polynomial function's graph will have at least one less turning point than the degree. Now we're going to look at end behaviors. A constant function, remember, is y equals some number, and it is a horizontal line. So its end behaviors are as x goes to negative infinity, y doesn't move at all. Same with as x goes to positive infinity, y doesn't move at all. But when we have a linear equation, y equals ax plus b, we have a sloped line. And this one, as x goes to negative infinity, my y's go to negative infinity. As x goes to positive infinity, my y's go to positive infinity. We're going to look at quadratic here. This is a quadratic, so as the x's go negative, the y's go positive. So right here I have, as x approaches negative infinity, y approaches positive infinity. And as x approaches positive infinity, y approaches positive infinity. They're both going up. But when you write end behaviors, you always must use this notation for end behavior. Now let's look at a cubic. As my x's go negative infinity, my y's go negative infinity. And as my x's go to positive infinity, my y's go to positive infinity. And then when we look at the quartic, as x's go to negative infinity, these y's are going to positive infinity. As these x's go to positive infinity, these y's again are going to positive infinity. So do you notice that both the quadratic and the quartic's end behaviors are the same? So when the degree is even, then the end behaviors will be the same. Now let's look at this quintic. As x goes to negative infinity, y goes to negative infinity. As x goes to positive infinity, y goes to positive infinity. Do you notice that the end behaviors of the cubic and the quintic are the same? So when the degree is odd, the end behaviors will act opposites of each other. In other words, if you notice, this had a positive leading coefficient, as well as this one. When x goes negative, y goes negative. Negative, negative makes a positive. As x goes positive, y goes positive. Positive, positive also makes a positive. Likewise here, negative, negative makes that positive. Positive, positive makes that positive. That only happens on odd degree. Again, on even degree, the ends were the same. Positive, 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 with a positive leading coefficient. So here I've just put those words down. The degree of an even means both are rising, which would mean y's go to positive infinity, or both are falling, y's go to negative infinity. When the degree is odd, the end behaviors are opposite. So as y went positive, when x went positive, when x went negative, y went negative. So in the end, they're different. Also, with the even degree, positive leading coefficient, both end behaviors rise, which means the y's go to positive infinity. With the negative leading coefficient, both end behaviors fall, which means y goes to negative infinity. And again, that's with your even degree. When your degree is odd and you have a positive leading coefficient, as x goes negative, y goes negative. Negative, negative. As x goes positive, y goes positive. Positive, positive. But when the leading coefficient is negative, when x is negative, y is positive. Negative, positive makes negative. When x goes positive, y goes negative. Positive, negative makes negative.
This portion of the CBS Evening News is sponsored by AstraZeneca. Visit us at AstraZeneca-US.com.
This one says, state the leading coefficient.
It changed my life, but I'm a survivor. After my heart attack, my doctor prescribed for
The degree,
people who have been hospitalized for a heart attack.
and the leading term.
With a low dose aspirin, no more than 100 milligrams.
Then, end behavior. So, sometimes it's easiest to find the leading term first. My leading term is the one with the biggest degree. That's my entire term. So it is a negative x squared. So the leading coefficient on that is the negative 1. The degree on that is 2. So we have an even degree with a negative leading coefficient. So as x goes to positive infinity, y goes to negative infinity. As x goes to negative infinity, y goes to negative infinity. So if we think of a negative x squared, it would be something like this. Okay, again, leading coefficient, degree, and leading term. The leading term is x to the 7th because that's the highest exponent. So the leading coefficient on that is 1, and the degree on that is 7. So a 7th degree with a positive leading coefficient will do something like this. So as the x goes negative, the y goes negative. As the x goes positive, the y goes positive. And the last one, leading term, that is a negative 3x cubed. So my leading term, negative 3x cubed. The leading coefficient of it is a negative 3, and the degree of it is a 3. So a negative cubic would do something like this. So as x goes negative, my y goes positive. That's that. Negative, positive. As x goes positive, my y goes negative. Positive, negative makes that negative.
You don't have to go through this alone. Call 211 to be connected to the resources and services you need.
All right.
If you're having thoughts of suicide,
This one says
Suicide Prevention Lifeline at 1-800-278.
number of turning points,
All calls are answered 24 hours a day.
degree,
Locally by First Lake.
leading coefficient, positive or negative. And then it says match the equation, give me the x-intercepts and the local max, local min, absolute max, and absolute min. So I see 1, 2, 3 turning points. So that means I have to have at least a 4th degree. My leading coefficient is going to have to be negative, since both end behaviors are negative. My x-intercepts are at about negative 1.50, 0, 0, and 1.50. My local max looks like here at about 1, and here at about 1. My local min, not applicable. More negative infinity. The absolute highest it reaches is 1. The absolute lowest it reaches is not applicable. However, here, I do have a local minimum. I need to come back here and change this. It reaches a local minimum here. This is where the graph is low. So that's at about 0. Okay, same thing on this one. Turning points, degree, leading coefficient, x-intercepts, local max, local mins, absolute max, and absolute min. All right. This looks like 1, 2 turning points. Very similar to an inflection as well. An inflection would just do this. It just switches its concavity. One inflection point acts like 2 turning points. So that means my degree has to be a minimum of 3. My leading coefficient has to be positive, because as I go negative, it goes negative. Negative, negative makes positive. My x-intercepts. Looks like I have one here at about 1.20. Local max, the highest points on the graph, if I'm counting those as turning points that high, is about negative 3.9. Local min is just right there. Looks like at about negative 4. Absolute max, not applicable. It goes off the graph. Absolute min, also not applicable, because it goes off the graph. And then let's get this last one, and then we'll match the equations. Turning points, degree, leading coefficient, x-intercepts, local max, local min, absolute max, and absolute min. I see 1, 2 turning points. So the degree has to at least be 3. Leading coefficient has to be negative. Since as I go negative, this graph goes positive. Negative, positive makes negative. X-intercepts looks like negative 1, 0, 1, 0, and 2.70. Local max. Looks like it reaches a maximum right here at about 7. Local min right here at about negative 3. Absolute max, not applicable. So it goes off the graph. Absolute min also goes off the graph, so also not applicable. All right, so here we said we need at least a 4th degree. So 4th degrees at least has to be even, powered. So that would be this one. So this one is f of x equals 2x squared minus x to the 4th. This one said at least a degree of 3. The positive leading coefficient. Well, this is a degree of 5. This is a degree of 3. This one has the positive coefficient. So this is f of x equals x squared plus x cubed minus 4, which leaves us at least a degree of 3, well, a degree of 5, and an odd degree with a negative leading coefficient. All right, now these say to go ahead and sketch the graph. I need a degree of 2, so that means 1 turning point. And my turning point happens to be at negative 1, 2. Negative 1, 2, right there. This graph must pass through negative 3, 4, so I'm going to plot that. 2, 3. Negative 3, 4, and 1, 4. So since this is where it turns, it must go something like this. This one's a degree of 5, an odd function. So that means it must be symmetrical at 0, 0. 5 x-intercepts and a negative leading coefficient. So that means as I go negative, I must go positive in the end. So all right, this one looks like it is at about 4, 2, 3, 4, 1, 2, 3. So let's see. This one is 1, 2, 1, 2, 3. So I must go 1, 2, 1, 2, 3 down that far. And then up to 4, 1, 2, 3, 4, up 3. So that when it rotates around this point, I have this exact same thing here as I do here and here as I do there. All right, this says interpret the turning points and estimate what they are. So it looks like I have a turning point right here. So it looks like I have a turning point at 1.5. This is in hundreds, so that would be 3,600. Then I have a turning point here at 3. Excuse me, this one would have been 360. 3.6 times 100 is 360. So this one was 120. And then this one looks like it is 4.5, 360. Now interpret those. So it's like running crushers. After 1 second of the timer, I was at 0 feet. Then after 1.5 seconds, I ran out to 360 feet. After 3 seconds, I came back to the 120-foot marker. Then after 4.5 seconds, I ran back out to the 360 marker. And then after 5 seconds, I ran back to the starting line.